So what I do in my company is I do HPC stuff. HPC stands for high performance computing. So we deal with low latency manner of code because the market is so fast. So we have to act fast to actually process this. And then we not necessarily need to be fast. We need to be low latency because market sometimes can be inactive. Sometimes it can be very active. So we need to process these packets as fast and then as responsive can. So most of the time when you heard about electronic trading, it should be buy low, sell high. I mean, how do we earn money? Yes, we do buy low, sell high. That's how we earn money. And then one of the way we want to earn money is actually doing arbitrage. You act faster than people to buy things in a cheaper way, and then you act faster than people to sell it in a higher price. So that's how we do. But a bigger chunk of our life as an electronic trader, we are doing market making. So that's why I need to explain to you what is market making. So let's say, if you are a Lord of the Ring fan, if someone wants to buy something in real life, not in Lord of the World, not in the Middle Earth thing, in the real world, if you try to buy something, and then if there is no seller, what will you do? You can't do anything because there is no seller to sell you things. So that is someone needs to be responsible for selling you things to make a seller of this thing. So in order to have this kind of trades happen, you have to match these two orders, buy and sell things. So a market maker comes up is the one who doing like a supermarket. He hold the inventory for you and then to sell things. Yeah. So the risk they got is the inventory risk because you buy something and then you need to sell it. You hold it, you need to hold it, and what if the price drop and then you have to sell it? Means that you buy high and then you sell low. That is the thing. So what we do is we provide the liquidity because someone, if they want to sell things, they don't have a buyer, then how? We provide the liquidity in the financial market. And then second thing, where in software engineer perspective, it's our requirement also. We are highly sensitive to the price and the offer price of the market. So we need to keep eyes on it. We need to listen to a WebSocket of it from the exchange. There will be a market feed coming to us, and then we need to process it and all this. So that's what we do. For the price update, if you want to do the cross exchange, they got at least 3, okay? And then for those assets, if you want to process multiple assets, you must have multiple WebSocket of it from different exchange, from different endpoint, maybe from different data center and all these things. So we have to listen to, for every trade, we have to listen to all the change stream or the book stream, and then once you execute, it got the update to us, the execute stream. So the crypto exchanges will make a lot of WebSocket connections. So this kind of connections, it may be easy when you are doing in node in an asynchronous way, but if you are conscious about the latency, it may be a problem because let's say you have hundreds of WebSocket connections and then you are keep pulling the sockets to see if there is an update or not in the system way. In the OS, you need to keep pulling it and all this. So for us, So for us in Rust, there is one library called Docker. For Docker, it is the de facto implementation in Rust. So when you are in Rust, people will talk about asynchronous. There's only one mainstream implementation, which is Tokyo. It almost monopolizes the whole ecosystem. And then for Rust, yes, we do have a syntax for the asynchronous programming. That's the async and await, just like the JavaScript. So so people who write JavaScript will find the Rust is actually quite interesting, familiar, because we do have the async and await. And for function that requires you to await things, you have to current it. You need to prefix it as sync. So this is a sync function. Inside it can use the await. So what does the async await does is inside await, you purposely tell the OS, not tell OS, tells the program to wait for it to happen. For this, it's a synchronous block. Whenever you use the await thing, the process won't be processed until there is a WebSocket connections packet coming in. That is what you do. In the async, the receive method is actually a sync function. That's how you can await it. So you await it, and then if there is some message, then you process the message. So why will people use the Tokyo usually? Just like what you do in JavaScript. You want the task to be you want the asynchronous functions to be working as sequence. You await things so the next thing wouldn't be happen before this one finish. So this is how you do. Wait, yeah, the wait. What? Don't forget. Oof, don't forget. The await is actually not a method, it's just a syntax of await. Something like that. And yeah. So, okay, the third point here, the goal here is to eliminate the OS thread. There's one thing that works similar to this one, which is the OS thread. So you spawn the thread, it can actually work in background. But in here, the Docker is actually user space. Why is that? Because if you receive the thing, does anyone knows how Docker works? Alright. I think I'll just explain the OS threads and the Docker thing. So, if I am the one who write the OS thread, imagine a world without a Docker and without a sync. So we will spawn an OS thread, and then it will do the receive thing. And then once the receive actually finish, how do you know it finished? You keep pulling it. That is one system called, in C language, you need to tell the OS to pull the data from this file descriptor. Because you establish a web connection, you get a file descriptor. Whenever you open a file, you get a file descriptor. This is a file in OS that this is the handler of this task. So you can deal with this task. This FD is an unsigned integer number. You deal with this, then you get this thing. Bring it. In Docker, it not necessarily needs to pull it. Why? Docker do have two components. One is executor, one is the waker. Waker will pull for you. It actually will listen to the OS, listen from the event FD, which is another file descriptor from the OS. It not necessarily has to pull it because the OS will tell you this, notify you, and then the waker will wake up this Tokyo task. This Tokyo task, and then it will happen. Telling you this away, and then you can process it. So what we do when we got multiple web socket connections, because let's say we listen to 2 web socket connections, and then the frequency is different. One is 1 minute per update, and then another one is 2 minutes per update. Then you will blocking until the 1 minute. Because it's blocking, because it's blocking, so you need to blocking and then wait for it to happen. And then until the next line of this loop, you need to wait another web socket connections happen. So what we will do is we have a Tokyo spawn. We spawn this async task. Async move tells us that this is a computation that will be moved to a Tokyo trace with Tokyo spawn 1, and then that is the computation we do. So in the line 1, which is the second block, the line 1 is actually making a channel. There's a TX transition, RX receiver. So you receive things from the TX. So the TX will be, the line 4 is TX. The TX sends the message. And then from the 9, that is RX. RX will be receiving the message. So in the loop, we will wait from the MPSC channel to happen. So that this 2nd to 6th line will be spawned in the background. It's background moving, and then it's not blocking. Immediately, it will print this photo, this line out, and then in the loop, blocking, because it's an infinite loop, and then it keeps pulling from the
mailbox. Mailbox.
Yes, actor is one of the paradigm to actually deal with the asynchronous, but yes, this is something like actor. Yes, but this is more fundamental. For the actor, it actually needs to pass the message, right? It pass the message, and then the TXRX is actually one they call bridge to actually transfer the data out. Yes, yeah. Similar. Yes, it's how it works here. So we are dealing with the Tokyo runtime, and then there are some of the problems. But when we write like this, there will be some problem when we are dealing with the low latency. But if you are doing with the web server thing, this shouldn't be a problem. Okay, that's one thing. We let the Tokyo to actually deal with the time. How do they pull the data? How do they process the data? What if there are a lot of Tokyo threads and there is only one CPU who does the job? So the Tokyo will actually help you to manage all the CPU time slice. They will have a queue of all these tasks, and then when you submit a task, they will maintain a queue. The queue is all those the tasks result slot. So whenever there is a result, you will write to this slot, and then tells the Tokyo, okay, this slot happens. Okay, what if in the same time there are multiple slots get written in it? The Tokyo will randomly choose one, and then pass it to you. So in the loop, you try to receive things. It won't be so precise, as in you get the result. It won't be so precise because Tokyo will handle it for you, and it depends on the Tokyo runtime's characteristic. Okay, so that's why number 1 is a problem, because we let the Tokyo runtime to deal with the pulling timeout times, and then to let the Tokyo to do the cancellations of the tasks. And then because Tokyo will do it for us, we want to bypass it. We will use the try receive, which is another not blocking function. So this wouldn't be a risk. this receive wouldn't be a sync function already. We use a try receive. So what the try receive does is it will pull the result and see, oh, it's empty. So empty, what we do? We skip it. So in a BC loop, we try receive things, keep pulling it, and then check the result. That's what we do. But this will have a problem because we bypass the waker. The waker is the one who listens to the kernel's file descriptor, the event FD. So now we bypass it, we need to pull. It will occur a system call called pulling. Keep pulling the kernel and tell us what is the result of it. So this is try receive. And then I got a parenthesis here. Beware of the syscall spam because keep spamming the kernel. Second thing is you change the MPSC channel to the third-party implementation. Because why? From the first line, the Docker sync MPSC unbound is a part of the Docker runtime's implementation. It used the Docker's waker to do a signaling, to signal the another end of the process that, oh, I already wrote one data in it, so you need to fetch it. Await got a notification and then keep pulling it. So we want to eliminate this one so that our 8 to 12 line, this loop will be BC speed instead of await of the result. So there are a few data structure, this data structure. There are a few data structures that does this job without using a single await, which is these two, dash map and a cross beam. And then me in my company who test these two implementation already, and then there are a few of the pitfalls in there when you are dealing with the low latency code, which is the first one, the dash map. Dash map is actually a concurrent hash map. It's just like a Java one, concurrent hash map. So when you are dealing with multiple threads, it will include the thread sharding. It will shard all these part of the hash map into different threads. So when you hit the cache miss, you need to check from another thread. It will incur a latency, which is unexpected. So we try to avoid it. For the crossbeam, it got a tail latency. So what is the tail latency? I need to explain the tail latency for you guys. Tail latency is like, you guys heard of the P99, P95 percentile or something? Not Pentium. It's like the P stand for percentile. So when we are talking about, the web, there's a HTTP request, it takes like average is 100 milliseconds, and then sometimes you spike to 2 seconds. So the P99 is actually the max time you take it for the HTTP request. We say P99. P95 means the top 5% requests take how long. So the tail latency is actually the P95 to P99. So when we say there is a tail latency, means that there will be a spike of latency, which is expected from us. For crossbeam, this one, sorry. So the y-axis is the nanosecond of the time taken, and then the x-axis is actually the message, the number of messages. So we can see there are some spike of it, which is unexpected. So when we say tail latency is the latency of this graph. So this graph is enough to depict the idea of the tail latency. Okay, so for concurrent data structure, there will be a problem when we dealing with this. Okay, when we are doing the structural changes on the concurrent data structure, we will have to either block on the right side or the read side. That is confirmed because two threads are actually operating on the same data region. To either block the read, to tell the read, you block the write, and then you let the read operations clear first, and then you can start writing to it. Or you block the read and then keep writing things. So in the interval of writing things, you can read. So there will be some log or some atomic variables happen. In this case, the crossbeam doesn't introduce the log, and it introduces something different, which is the copy of the data. So it means you're writing things, and then you can keep reading it. But when you are doing the structural changes, let's say there is a tree, B tree map, you go another level, you are changing the structure of the tree. So what happened? But you keep reading the things, and then your pointer changes, you allocate things, you need to swap your AVL tree and all this. So what happened? It will copy another copies of the tree and then keep writing to it. But your read is keeping reading this version. So until this finish, and then it will read this one, the second version. So it won't have log, it won't have the latency changes. Then you have to pin the thing. So when you are copying things, you basically have to manage the garbage collector. You need to manage the garbage collections of the copies because you keep writing things, and then if it changes a lot, it will create a lot of copies. So you need to delete all these copies. So the crossbeam does have the pin number 128, and then when you are dealing with the pin thing, you will increment the number. So that is how it works. So the spike is actually caused by the garbage collection. Even though you are writing Rust, but you introduce a spike due to the EBR, epoch-based reclamation. You reclaim the copies of the data based on the epoch, based on the version number, EBR. Okay. So this is the pitfalls of this true data structure, and then the problem that we face when we are dealing with dog cures and all these things. As channel, MPSC channel stands for multiple producer, single consumer. You got multiple produce a message, and then you got one reader keep consuming it, keep dropping the message when you write the lead. Okay, we need something to pull the result and the system call. So these two problems is actually the pooling. How do we pull the data? And then how do we deal with the system call? So uring happens. So uring is a very new ways of dealing with the asynchronous, as I stated in the beginning of the talk. So what does the uring do? Uring is actually have two ring buffer, which is SQ, CQ, which is a short form of the submission queue and the completion queue, which is people will use this shorthand to represent these two ring buffer. So for this ring buffer, when you are dealing with the task, you need to submit the task. On the contrary of the Tokyo is a pool base, because I keep talking about pool the result. This one is a submission. You submit the task, and then you pull the data which the asynchronous operations finish. It will write to this completion queue. So you pull data from this queue. And how does it work is you got the init params. These parameters is the parameters to create these two things, and then you call this function from the lib your uring. You call this thing, and then it will occur system call 3 times. MF. With this 3 MF is the SQ, CQ, and the SQE. The SQE is an array of the data which store all your operations. So MF is a memory map. A syscall to tell the kernel to give us memory region. So you use these 3 memory regions to create the SQ, CQ, and the SQE, which is an array of the tasks. And then the kernel will maintain the pointer to this CQ so that whenever the kernel finishes a task, it will write things to this CQ. And then you are the one who is responsible to pull the result from it. So how do we submit a task? We create an SQE, which is the submission queue entry to call this function, to submit to it. And then what is the operations that support in this one? Basically, there's all the system call you can submit to it. It's like a proceeding. So we wrap the system call with all the parameters, all the arguments it needs, and then you submit to the SQ. Let the OS, let the kernel enter. You tell, now you already submit to this SQ, you tell the kernel to read it. It's like to put something in it, and then you tell the kernel, okay, you can start to process it. This is the uring enter. It will render the kernel. So when you are dealing with the WebSocket receive, when you want to write something, write, the SQE will be write. When you try to receive things, let's say you want to listen to a WebSocket connections, accept, get the file descriptor, then you submit another SQE, listen, receive. They keep receiving the data. So this is how we do in uring. A few moments later, then once the task is finished, how? So this is a CQ. From the CQ, you can pull from it. You can get the completion and then the simple loop to iterate this ring buffer, taking the CQE, which is the completion queue entry, taking all these tasks from it. So yeah, easy pulling. So you will have a trick to easy pulling, pull all these data out. You don't necessary to pull the kernel. You don't need to make a system call to the kernel, tell them, hey, when is this task finished? No need. You just take from this one. And then if there is no, then the loop will continue. Yeah. And then the structure of the CQE in Rust, that is quite complicated because I read from the code. It's quite complicated and it is a wrap of the C libraries. So right now you have to read from the menu, the Linux main page and all this to get the actual CQE. But here I am, I compile it for you. So if you look at the main page or the source code of the Linux kernel, it's actually this. It's that simple, it's this. And then for the user data, is actually the unique ID that's set by the SQE, which is the one who set by you, the user defined one. So when you submit a task, you have to specify the unsigned bits number to it, and then the task finish, task back to you, the user data, you based on it to index the task that you created. And then what if it is some buffers and all these things? It's not defined by the and then got lost already. And then for the result of the task, when we repeat, it doesn't define here. When we repeat, then you need to read from the main page. Let's say you need to read from the main page because it only gives you the result and the flag. So for let's say we want to receive something at the main page first, you try to receive something, and then this is the you based on the flag, you do the buffer select the flag to get the thing you got in the buffer. What buffer is it? So this is the buffer pointer. So you have to give it a buffer to it. So you need to allocate it yourself and then pass the pointer to this operation and do. Basically, this is a system call, which is very low level, and then it's not meant to be used by normal developer. And then for us, there is one wrapper functions in Rust that you can do. So it takes the flag and then returns you a number, which is the number of the buffer site you need to get. Okay, back to this. So this is how we query the result from the kernel. So why is it so important, and then why am I keep emphasizing it? Is because the layout of this IOU ring is actually represented by this graph. So this is the user's, the left side is the user space, and then the right side is the kernel. So whenever you are the one who set up this IOU ring, you actually create SQ and the CQ. The SQ and the CQ on the user side, you can access it from the user side. Basically, it's a pointer. You can access to it without any logs, without any system call or anything. But the kernel does have the pointer to this CQ, and then the IOU ring instance does help you to manage this memory region. And then it is directly writing to this one, so you don't need to pull, you need to make a system call to pull the result from it. And then when you are looking at this, yeah, you can publish the syscall to the kernel, and then the kernel will help you to arrange all the system call. It's basically a serialization of the syscall. It's like a bus. It's like a bus. You tell the kernel to do stuff for you. You manage all these tasks together in a sequence, and then it will help you to finish it. And the result may be not in a timely manner, but you can actually pull it from the CQ. So, time so fast. Okay, faster, sorry. So what do we do? Because we serialize all this and then let the kernel to actually process this, or we reduce the context switch. The kernel don't need to switch to this kernel or switch to that CPU to do tasks. It's all single threaded. So we reduce the context switch. We reduce the system call because we got lesser system call to pull the result from it. And then we got zero copy of data because the kernel is responsible to write things directly to the CQ. So when you are dealing with all these WebSocket connections, you are dealing with the RESTful and all this, you can create multiple IOU ring. You create multiple IOU ring, then you got 2 ring buffers you need to iterate. So when there are a lot of IOU ring, you basically become the Simuliu, which is the Legend of King ring buffers. Yeah, it's that efficient. And it's like a joke in my company because I deal with like a lot exponential growth of the ring buffers. So I call myself.
No, face the issue like memory, access limit, like that.
Yes, you can actually use a command line to make it as high as you can. Basically,
yeah. You can adjust the size of the ring buffer.
Increase the size, like increase the memory.
No, not only memory size but also the file descriptor limit, because you create a lot of file descriptor during the initial state. Yeah. Which is you won't face this problem number. So that is how I got the information. There is one menu written by the Meta developer, which is formerly Facebook. He is the main author of this uring. So he does manage this website, which is quite easy to be Googled. If you type a lot of the uring, you will get this page. Basically, my idea of the site is taken from this. So this the site very useful. It's like MDN for me. Whenever you got a problem with the uring, you browse this, and then you can easily Google it. No, my slide is not finished. So when I tell my bosses, yes, we already reduced a lot of system call, but unfortunately, there are still quite a lot of system call happens. It's nearly zero, but it's not zero. Why is it? And then I tell him that, okay, because here we receive things, and then it's only used one. The system call is only used one. So if you want to reuse it, you need to submit another call receive. Let's say we need to keep looping, keep receiving a message from a WebSocket connections. You need to keep submit this receive into this uring. Keep on going, keep submit. And then whenever you submit it, you need to call this system call, uring enter. So my boss tells us, why can't you be optimize it out? And then I said, actually, yes. So this is how I optimize the uring mechanism, because uring is so flexible, it can help you to optimize things. So these are the three methods that I use: zero copy send, zero syscall in hot part, and the buffer receive. So the first thing is zero copy. So there is one API in the Linux called scattergather, and then in Rust term is in programming language term is the vector IO. So basically, you have maintained an IO vector of these things, and then what is it? It is like a pointer to a string. So when you try to send things out, there is a string, but you not necessarily need to pass the string to this system call. You can pass the pointer to this system call. What your string needs to be concat? Pass multiple string pointer to this system call. That's how the scattergather system call work. So yeah, there is a send message ZC. ZC means zero copy. So we receive the IO priority things. So you can actually pass this IO vector to it. So IO vector is the vector of these pointers. So you can actually pass a pointer of the string instead of pass it. So because you pass it, you need to copy it to the kernel. First thing. Second thing, zero syscall in the hot part. So yes, because the thing I said, you need to keep enter the uring to tell the kernel I already submit the task in SQ. You not necessarily need to do that, because there is a flag called uring setup SQ pool. When you set this, wow, your CPU usage must set to 80 or 90 something. Why is it? Because that is the background thread helps you to pull the SQ in kernel. So you don't need to keep calling the uring enter to tell. It will have a spinning loop to spin in the kernel space, keep looping the SQ for you, the kernel states. So you no need to enter. Okay? And then there is one thing. When I use this, it still got the uring enter, even though it is almost empty in the SQ. So I look into the menu, and then I see why. Because there is one parameter called SQ trade idle. This is a timer. So whenever there is no IO uring enter, it will help you to do this. So you will set it large enough so the IO uring instance will not help you to call the enter again. So that's what we do to make 0.6 call. Another thing is the provided buffer. So provided buffer is a very new thing, which happens to be the last year feature from the X. I'm not sure how to name it, how to spell its name, but Expo. Okay. James Expo. He's the main author of the IOU ring. He does provide us the provided buffer feature. So provided buffer is like you receive things, but now you can get multi-shot receive. You receive, so you only need to submit one, receive multiple, so you can keep receiving all this. So you don't need to tell the kernel to keep. No. It's like you don't need to resubmit the receive in kernel. It will help you to do this automatically. So you can save more CPU instruction call, right? So it's quite complicated, and then I just tried it out. But what we got is the QPS increased about 6%, and then the latency also drops also. I don't have a benchmark of the latency, so that's the thing. So the user provided buffer is also provided by you. You need to map yourself and then provide a pointer to this system call receive multiple to get all these things. So it's also residual in this space also. So what is the cons of it, provided buffer? The cons of it is you may be getting batch message because you keep receiving it in one notification. So you notified by the kernel. Oh, you pull from the CQ, yay, and then you got what? You got a batch message. So, and then it's very low level. So the first thing I got is why I can't deserialize it as a string. So yeah, you have to decode it because we are using WebSocket secure. You have to TLS decode it. So you decode it, you got the message, then see what you got. When the market is busy, we will get the batch message. You can see from this, but then you can see some of the invalid URL code. Why is it? That is because of the WebSocket frame. The WebSocket does have the header, so you need to calculate how much length the WebSocket is to slice this into multiple message, and then you need to calculate how much length the WebSocket header is to remove the invalid characters. That's how troublesome it is. So yeah, the final part of this call is actually how are we integrate in the Rust, because this is still a very native ways of handling the IOU ring. Although Rust does have a single way, but for Tokyo, as I said, it's pool based. But in this system, it's actually submission based. You not necessarily need to pull things. Instead, the way you submit things matters. So Rust does have some debate in the community, which is the async read, write, and the pull stuff. So I think you guys can actually read on the comments, because for me, I'm not sure about what is the point of their debates and all this, because their debates talks about how do they pull and read things, and then how should I explain this? The IFC, the idea of IFC.
Request for comments. Like they want to get feedbacks on the design.
Yes, they need to get the feedback from all these users and all these the communities, and then discussion will actually dictate how we write code in the future. So it is also quite new, and then quite new. Quite new. See, okay, the debate is quite old lah. They talk about really long time already. I don't know what it means. Okay. So there are some traits in future they will be integrated in Rust to properly to suit this submission-based asynchronous model. So let's see how they do lah. I can say this, but in the meantime, we can only use IOU ring like this, submit the greetings instead of the traits because it's not so mature in Tokyo. And then for Tokyo, the backend is not necessary IOU ring.
It's not only in the way in Rust, only in there, in the way in other programming languages, not only Rust.
I think not sure in other languages.
So this C but it's more mature, right?
Of course, man. The Linux is the C. The library is written in C, so it will be more mature. But in terms of the framework and all these things, basically it's not integrated in the Node.js, so you can't see it in Node.js. Maybe Dino can. Maybe Dino have this.
I can call using FFI, right?
Yes, you can call it FFI, but how do we actually integrate? Because the paradigm of how you submit the async task is different than how Tokyo is. Oh, paradigm is different.
I'm asking for like the language support, please support.
Language support lah. Higher level.
Yeah, IOU ring.
It's very low level. Ada yang high level lagi kalau kebet dia built-in runtime. So if you use any dia
I think .NET will be more mature because .NET they are using the Windows asynchronous I/O also. There's one called IOCP. IOCP is also submission based, so it probably more suitable more sure no need to have big changes in the framework and all this, and then can adapt to this more elegant.
Kalau nak guna tu guna library lah. So dia depends dengan library apa kau guna. Bagi contoh kalau orang guna .NET, macam saya background. So dia ada yang famous kalau orang guna pakai library lah. Dia macam soft JSON. Tapi yang kedua contoh system text JSON lah. So it's a library yang Microsoft official sendiri pun ya ada di komik terdapat tu. So depan guna lah. Tapi kalau dapat di library selalunya dia tak berapa.
How does it translate? Because I already use the Linux specific implementation. So how does it translate across? For example, Rust is a platform.
Platform.
How does it translate across?
Kalau dia kompan biasa ni, so orang tahu
Back to
ya
what
specific system call. So different OS ada different system call dan different mechanism sebenarnya.
So for example, if they implement in Tokyo, so it will use OS specific.
Tokyo doesn't use IOU ring.
Tokyo doesn't use IOU ring, but basically the Tokyo is, let me see, executor reactor. So basically Tokyo, when you want to change it to multiple platform, let's say you want to make it in a BSD, or you want to make it in Windows or Linux, this is the one you need to change because this one will wait this executor. All this higher level logic is still in Rust. It's not platform dependent, but the reactor is platform dependent, so you need to change code in here. But as I said, the way we pull things and read things and then to pull from the kernel the result, how does it happen? The logic is not suitable for the IOU ring, because IOU ring is totally different. It's totally different. It's not pull from data. You need to have another, maybe the executor here needs to have maintain the CQ, keep looping, and then return to the task. Change it up. A lot of need to change.
Yeah, I can explain a bit more as in, the IO, right? There are two types of IO. One type we call it pole based, like it mentioned is pole based.
Yes, this is pole based.
And then the other one is completion based. The pole based we have ePole, KQ, and IO. ePole is the one implementation Unix based system, and Windows have their own stuff as well. Here, because Tokyo is the model of the Rust async await is based on more like polling kind of logic. So that's why here Tokyo uses the polling based systems. And algorithm is a different mechanism which is based on the submission based. And the difference is that poll based you keep polling, submission based you submit a task, and then once the task is done, you don't and then you get from another place, which is like less system call. That's why submission based is faster, and then the polling based is you need to keep sending system call to get the result.
And then even for the async await syntax, the async await syntax in Rust is actually based on the future task. So there is one library called future for S or not? Future Rust. Yes. So it's based on this one also. So this one does have the pull ready or not ready, which you won't see that in IOU ring, because IOU ring you got this result already. It wouldn't be not ready. It wouldn't be none. You already got this result. So all of the async await stuff in Tokyo is built on top of these futures. So if you want to reuse it, pretty hard lah. I can say that you not. So if you want to use that, you can't use the feature. That's I think my slides. And here, that's my company's name.
So is there any questions?
Yeah, so now we have Q&A session.
Q&A session. I know it's very tough. Yes, come.
So now you have two queues, one for submission or for completion. And okay, you submit something and you get it that it's done. And then you have to request another system call to get the data, right? Where is the data?
The data is you need to provide it. The data, let's say when we are dealing with the provided buffer, you need to provide this buffer.
So it will be like an empty.
Yes, it's an empty array. It's an empty array. So you need to tell the IOU ring how big it is, how many slots it is. So whenever you receive a thing, it will write to this buffer in one slot, one offset. It is basically it treats it as a ring buffer. So it gives you this thing, and then in the CQ here, you got the flag. You need to buffer select the flag to get the index of where the data is in your user provided buffer. So you index from it, pick it up, that is your data. That is your data, then you complete. Yes, this is how it works. Or if it's small enough, let's say just a single receive, you can get the data from the pointer, based on pointer. So you dereference the pointer, you get the data already. So it's also in the CQ. If it's small enough, it's in the CQ. If it's not, you throw error also.
How about the Gromio, which is like a high level?
Yes. There is one Gromio. It's also a runtime. It's also a synchronous runtime written by the Datadog, which is, for me, is a very good startup it do the data visualizations. It also have a so-called runtime, but the runtime is actually different than the Docker. It also use IOU ring. Utilize IOU ring, so you can actually write a single await, but in the backend, it is using IOU ring to do a task, and then you just pull from you. So when you pull from you, yes, it will have a memory limit. So when you use this one, you have to increase the memory limit max lah, something like that, because it helps you to pull things, and then it uses a lot of memory to help you to pull things. To answer the questions, it basically have another layer to help you to pull things in this graph. In this graph, it have an interpreter layer to do this for you. So whenever you get the pull ready stuff, you get the things. But the backend is IOU ring. 没问题 ，mind blown. Question?
One more question, just wondering, whether this is a big or marketing. Because from what we know, when they write the constant models, such as Taylor Swift, there's a huge traffic and a lot of people they are looking at for traffic. Most of the people they are not in the they are not passed into to buy. So my question is this IO really you just wondering, is this IO really time to solve the problem or what?
I would say it's probably like a scalability problem. Scalability. If you have a scalable software, if like there's 1 million concurrent users, and maybe if you can scale your web servers to like maybe 1,000 web servers in a short period of time, I think you can handle those. I don't think it's like unless you want to cost optimize like your scaling solution, like I really want 100 servers, but I want to serve 1 million users. In that case, you have to like optimize every path that the backend travels. So maybe one example might be using library in some of your application, but I think the quick solution to like handling 1 million concurrent users is probably just scale your web server. Yeah.
I think it's a very good interview question.
How does it solve all the same? Usually the use case for something like this is more like where we cannot scale our hardware. Yeah. For example, like in play games. In play games, you cannot ask the players to open the computer. You have to open your game through what. So that's when the IO whatsoever is coming up. You have to optimize at application level. But for like Taylor Swift whatsoever, you need to have a proper software architecture because no matter how professional, how good you are optimizing your application, there is some limit like what you can do.
In this case, you don't really care about scalability, right? Just care about latency.
Yes.
Yeah. So it's because the one that's really engine is just for your traditional beliefs.
Yes.
Okay.
All right.
So you just want to execute the tape as quickly as possible.
Yes. All right. So I think it's also part of the optimizations where can solve the Taylor Swift issue lah. So for the Taylor Swift issue, Billie Eilish or whatever the concept is, okay. You need to pinpoint what is the problem. So when it starts to have like C10K concurrent 10K connections, then your server down, then you need to see, oh, I'm still using a single connection, single thread, not single thread. One thread per connection, or definitely will crash one, because one thread you use like 4 MB of memories, you definitely will run out of memories. You need to solve this. After you solve this, then you see, oh, okay, your connections will take a lot of like memories, or you take a lot of physical. You keep pulling data. Yeah, you keep pulling data. So too frequent means slow. So you cannot handle a lot of users. So users will need to wait for your server to process all this, and then you solve it. You optimize by pinpoint where the problem is, one by one to solve, and solve the biggest chunk of problem first. So this is one of the way lah. Maybe the ultimate way, because if you got that problem, I think there will be that you can change your language stack, you can scale it, you can put Redis cache to something else, so you need to query the database. A lot of optimizations you need to care of.
It's more like last method lah, like very niche.
Very niche. Very niche.
I think this is much more suitable in a real-time scenario use case, right? Can you say that? Like if
Yes.
if there's some real-time computation needed to be done, for example, in Taylor Swift, they want to track how many people bought tickets real-time. Like they can go to the website, see now we have 100,000 of tickets sold real-time, and the number is legit. And those kind of scenario use cases, maybe you can use IOU for that.
Yeah.
Real-time, whereas in my field is more like, press a brake, your car must brake now. This is technology.
They do. Yes. Yes.
Question: how much faster?
I am not sure about how much faster, because if you want to measure how much faster, you have to actually look at the time, the kernel flag. They will have a time when does it receive. Because it may be because how do I say this one? So it depends on how so the time I observe is when I take the result from the CQ. Actually, it is maybe seconds. Back then, the kernel write to the CQ. So I don't have any way to actually observe that timestamp yet. But we do have reduced the system call to 0 during the programming hot part, and then we natively compare from the 800 microsecond down to 8 microsecond. So it's like 100. 10,000% what is it called? Lower latency? Lower latency. Yeah. So I think there's a win for us. I think the biggest win is actually how we write the code, how we structure the code. That is the biggest win, because this is the pain point here. Other thing is just a bonus point. It's the biggest point when I'm dealing with a lot of conditions and keep creating the doctors, traits, and background traits, all this.
Why do you need to create multiple LU rings? Like, why not one LU ring and then submit all the tasks, distance, throw there, and then...
Good question. I'm that ambitious to make it as one, but for every ring, you got a lot of system call there, right? You need to index all the... Wait, I forgot it. For WebSocket, let's say for WebSocket, we will maintain the user data. Back then, we will maintain the user data. For user data, we submit the user data, and then we identify it by the user data from the CQ. We will mess up, because when I want to do the RESTful, I also use this LU ring. So I will mess up this. Better than I just create 2 LU ring instances, one to handle all these WebSocket connections, one to handle all the RESTful connections, RESTful and all this. It's better for me to create, because it creates cheap. Grade 1 is just cheap, but maintaining it,
You keep track of.
yeah, you keep track of all the user data. Troublesome. Creating more is cheaper and then more easy to manage.
Any other questions? Oh yeah, there's one question.
I was wondering, like, the different, the main problem in Tokyo, like, one, yeah, this one, right? So this one, Tokyo Thread, is it same like we create the OS thread?
It's similar to create the OS thread, but the difference is we let the Tokyo will have to schedule this task. But when you do the OS thread, it will also OS does have a scheduler. This depends on you want the Tokyo to handle for you or you want the OS to handle for you. But OS is more expensive because OS will schedule CPUs, schedule all these contacts.
Tokyo, we do the syscall, I don't see like, so by using uring, do we reduce the syscall to the kernel or just that depends on the situation? You get what I mean? Like, the main point here, we want to reduce the syscall. Or
Yes, the main point is reduce the syscall, but in here we are not reducing the syscall. From Tokyo switch to uring is actually we reduce the context switch because for this one, the Tokyo spawn, the Tokyo will come to this task, it will somehow pull from an internal state, and then it will come to this task, it will also pull from this. So when it starts switching this task, it will have a context switch also. Now, what I say is serialize the system call is because we're using one loop to handle all of this code to reduce the context switch.
Okay, I say more a bit about the Tokyo. The Tokyo spawn is a green thread. So Tokyo runs on green thread. The Rust setting away runs on green thread.
It's like go routine.
Yeah.
It's go routine.
And then and Tokyo there's another spawn. They call it the Tokyo spawn docking. Tokyo spawn is used for the IO based task, and then Tokyo spawn docking is used for the CPU based task. You know when you are running performance sensitive code, you need to differentiate whether the task is IO bound or CPU bound. Let's say if it's CPU bound, then you throw it into the spawn docking. Then spawn docking will spawn like a system thread. They'll use, I don't know whether they will spawn another system thread, but most likely they'll use a new system thread, AD thread, and then they'll run it there. And Tokyo spawn will spawn the green thread. Green thread you can spawn when it is very cheap because green thread is managed on the user space, and system thread is a bit more heavier to create. So I bound task you spawn, and then CPU bound task you do spawn docking.
But I can gather from this, I have to go back home and overwrite my OS as well.
Yes. CSAPP. Start to read CSAPP.
I have to, oh, this one, legend.
Legend.
Legend book. We have to go back again.
Guys, any other question? No question, then we'll probably end our talk. Okay. So thank you, zypeh, for this insightful talk. Right. So now okay. So